Hello. Hello, everyone. Thanks for coming on our seminar. It is a great pleasure to introduce, well, there are no introductions for our speaker today. We have Professor Jose Castillo. For some of us, it's just Jose, the director of the CSRC, who is going to talk about solving PDEs using the model library.
Thank you. Basically, what I'm going to do is now to be current with the situation we live today. I'm going to do a drone view of the library and how to use it. Okay? So it's a very high level thing. So it's not that much details, but I believe that all of you or most of you have already used the library for sure. Okay, so I'm gonna make a little introduction, talk a little bit about mimetic method, and mostly what are the main properties, things like that. And then I will just go into looking at PDEs, the way you get a PDE. If you go to Home Depot, you buy a PDE, they give you in a particular form, and then you change it so that it is, let's say, that to use the mimetic operators straightforward from the library. Okay. Okay, and please stop and ask questions anytime you want. Okay, so basically, mimetic is actually, I think this term was coined by Mac Hyman in Los Alamos National Lab, and basically, mimetic comes from imitation. In English, mimicking is imitation. So basically, the idea of the philosophy, in some sense, of mimetic method is that instead of taking the PDE, for example, you find a difference, you take the PDE, then you approximate the derivatives by something, or if you use finite elements, you assume that the solution can be written as a linear combination of some functions, and then you use that to discretize the PDE, and at the end you solve a system of linear or nonlinear equations, depends on the character of the PDE. The same thing with finite difference. In this case, we don't. So basically, what we do is we write the equation in vector form, and then we use what is called the scheme that we build is based on using these mimetic operators. Okay, and the mimetic operators are discrete analogs of the first order invariant operators, divergence, gradient, and curve. Okay, so and for that reason, we believe, and we actually, I think we have demonstrated that many times, that they're more faithful to the physics, because the same properties that they satisfy in the continuum, they are satisfied in discrete sense by this operator. Okay. Also, basically, I'm going to focus in the library that we built, and now I actually forgot to put it in there, but we got a grant from the National Science Foundation to transition our library into a software open ecosystem. And that basically we've been working in this to make it, well, more user-friendly, more better documentation, and also we're expanding the functionality. So in first phase, we're doing that. We're building documentation, and also right now, pretty soon, I guess this hasn't happened yet. We'll be able to install the library and the using make, and it will check all the dependency, operating system, everything. You don't have to do anything. You say, I want to use no. And we recently got it working for people who use Mac. I actually have a Mac, but I don't use Mac, and I use, if I'm gonna do anything, I use Linux through the Mac. But if you are a Mac user and you use something called Homebrew, then you can actually install it and do the same thing. Okay. So And mole actually is no mole like in chocolate. Is no mole from chemistry. This is actually mimetic operators library enhanced, and it's based on this underground creature, which actually is very smart and it works very hard. Right? That actually is the reason it was chosen as the symbol for the library. Okay, so as I said, and we have a paper that was published, I believe this year, in the JOS, which is a Journal of Open Source Software, where it's described a little bit there. But we have published quite a few papers using mole and without using mole for solving PDEs, different type of. Okay, so again, in this case, mole provides you the operator. We're talking space. By the way, that's one thing that is important to emphasize, I guess, that divergence, gradient, and curl has nothing to do with time. Those are space representations of this operator. When I use solve a time-dependent problem, then you have to use a time integration scheme in connection with this. At the moment, we also have some example in the library where we have time-dependent problems. Okay. So we one thing that is important to mention is that these operators are constructed over staggered meshes. Okay? And basically we use uniform, non-uniform, and curvilinear meshes. And we have also demonstrated that they satisfy linear and non-linear conservation rules. So when people say, when we say mimetic methods, those then basically is we're referring to the construction of these discrete analogs of divergence and gradient mostly. Okay, so and those, as I said before, these discrete operators mimic the properties of the continuous counterpart, and they have a metric representation. Now, there is one thing that is very important, is that if we look at these operators, okay, and by the way, you use find a difference, you can write as in matrices representing forward, backward, center. Okay, those will be the equivalent representation in terms of matrices. However, our operators have uniform order of approximation in the boundary as well as in the interior, and there is no other method that have that. Of course, if Ricardo will be here, he will start jumping that he can do higher in the boundary, but he has to do something else. We don't have to do anything. This is natural to the operator. Okay. Another thing that is very important is that these operators, for example, the divergence and gradient, they satisfy an a discrete extended Gauss divergence theorem. Now, there are people who construct methods, they actually call it mimetic, where they actually construct an approximation to the gradient or the divergence, and then they plug this into this equation, and then they solve for the other one. Okay, that's not how vector calculus works. Okay, so what we do, we construct divergence, and then we construct gradient separate. Then when we plug it in here, it satisfies the extended Gauss divergence theorem, like happens in vector calculus. Okay, now this the standard in a product, with the standard in a product, you cannot construct high order operators with high order boundary. Okay, if you do, for example, in general, most of the methods, if they are second order, they are first order in the boundary. Okay, and there are people who have fourth order method, then they are third or second. Versus in our case, I can do third if I want to, but we get fourth uniformly. And so we use a generalizing a product Now, as you are also aware, you got a general and inner products. In this case, is P and Q are numerical quadratures, are actually a real bona fide numerical quadrature. You can integrate with that. One thing that is important to mention is that all the coefficients in this is their diagonal, and also all the coefficients are positive. So that means it preserve the positivity of the solution. And what does it mean? That means that if you gotta solve a problem and the solution is positive, you're not gonna get something negative. And the solution is negative, you're not gonna get something positive. It will keep the same sign of that the natural solution has. And that's actually very important. There is a lot of quadratures which have some different signs, and there is no guarantees. Also, this inner product generalizes a norm. That we have a norm that is induced by this inner product. And that is actually the natural norm space where the mimetic operators or functions live. Okay? Now, of course, we all know that in the finite dimensional space, all the norms are equivalent. But some norms are more convenient than others for different things that you want to have. Okay? For example, the spectral norm is very convenient to do analysis, estimates, but it's very hard to compute. In this case, this one, we don't have that problem, but also we can use that to do estimates. And right now, we're starting to use that to prove results. Okay, as I mentioned before, we use a staggered mesh. I'm gonna illustrate this in 1D. We have an interval AB and we split this, then we take the cell centers, okay, and that's where the scalars live. Okay, we take the cell nodes, that's where the vector live, and the center extended. Actually, the scalars are in the center and also in the boundary. And that gives you a way to represent, as you can see here, the gradient is in the nodes, which is a vector, the divergence is scalar. So it goes in the center and so on. The mapping or the linear transformation, you got the one at the top is the divergence, go from the nodes to the center of the cells. Then you get the gradient, it goes from the center of the cells and the boundary to the node. And this d hat is just an extended because the divergence is not defined in the boundary. And then when you write the matrices, they don't have the same dimension. So in order to make it match, we actually add zeros, the corresponding of the boundary for 1D, and then they match, they have same dimension, and you can multiply dg, and then you get a Laplacian. Zoom 1D, 2D and 3D, they're little more complicated, but it's basically the same. This, I actually need to update this because this is true, that the operator satisfies the vector calculus identities in differential sense, and in the integral sense, with the proper interpolation, satisfies all this. However, we already can demonstrate that all the properties can be satisfied in the integral sense using the corresponding quadratures for the interpolation. Okay, but let's say, what is the benefit to society, by the way, which is one question that NSF asked about this. Because the way I present the library is that this is like a Lego. It's a building block. You have the library, and that could be used as a building block where you can write a very computational efficient code and accurate to solve a complex problem. And the benefit to society is the productivity, because if you have to write that thing by yourself, it will take a long time, a lot of lines. You're talking problems in 3D, complicated problems, the number of lines increase no matter what language you use. But if you use the library, then you already have all the operators in 1, 2, and 3D, and you just use it, and the number of lines is reduced substantially. So, for example, just 1D in MATLAB, for example, that you write, and you have to write all the stuff, you're talking at least 100 lines versus you're using the MATLAB, but also with the operators, you're like 5 lines of code, you get the problem. So in that case, it affects the productivity of the scientists because it doesn't have to, whatever, it simplifies the use. Okay, this is versatility, but also it's reusable. You just, for example, you write a code in curvilinear coordinates, and basically you have to change very few lines of code to solve other problems. They're reusable. The same code, you just make minor changes, you can solve it. Okay, so the library, like I said, is flexible. You can go in transition between different grids, resolution, order of approximation, discretization, and so you can tailor to a problem that you're working. And this is actually for anybody can use this library, but for example, anybody in science, engineering, has a minor understanding of programming can use it. It's not a black box, but it's actually very, how do you call it, usable. So, okay, for example, here is this example of a Poisson equation. So, and this is what I refer as, this is your PDE, the way it comes at the top. Actually, most likely will be Cartesian coordinates, not in vector form, but then you from there you write it in vector form, and then all you do is whatever you see as divergent, you just represent it with a D, which is the divergent of the discrete. The G is the gradient, and right away, what do you have? You have this, which is a system of linear equations. Okay, if the problem is nonlinear, you get a system of nonlinear equation. After that, you solve it anywhere you want. It could be a direct method, iterative method. Okay. And there are many, that's, I believe, in computational mathematics, that's where there has been more research in the history. It's about solving this linear and nonlinear system of equations that come from solving PDEs. So at the moment, we have also different boundary conditions, but we don't have, and this is, you really need to work to impose the boundary conditions properly. We are working in the near future to expand the boundary operator that we have that will be able to provide. You can just use it, but then you can specify and you will be able to get, right now for Laplacian, we can get directly all this, but we will have different, you have probably in 3D, you have different boundary conditions, different phases, you have kind of periodic boundary conditions in some phases or periodic in all of them. So that's in the near future something that we will have and that will facilitate. But you can actually use it right now, impose your boundary conditions. You have to be careful. And for the integration, for example, we'll show you something that, well, this is a sort of a curvilinear mesh, but basically it's a staggered mesh in 2D where you can see the same thing. How basically you can imagine the 1D and you start putting one after the other, and then you got a 2D staggered mesh. And then you see they have different colors. If you join those circles, then you can actually think of this as a dual mesh. Right? And first time when I started doing this, I used to write a mesh for the gradient and a mesh for the divergence, and then later I put it together. But at the beginning, I was just looking at them independent. There's no longer the need to do that, so everything makes sense. Okay. And this is a solution to that Poisson problem. And if we actually put it in one, it's actually one on top of the other. That's, the error is yes.
What order is the operator in approximate?
This one I think is probably fourth or second. So I don't have the labels, but okay. Here is this is from a paper that is already published. And if anyone wants a paper or something, I can give it to you. So, and this is, I believe this is the paper where we published, where we established P and Q as bona fide quadratures, and also we prove that they are satisfied the divergent theorem, okay? Which is and that's one thing that I've been looking for a while because I wanted to establish the mathematical foundations of the method. Because if you look at finite difference, so the only thing you can talk is about Taylor, basically. Now, here there is mathematics behind it. This is one difference between finite elements, because finite elements is based on solid spaces, so there is a beautiful mathematical theory behind. Of course, at the end, you don't want to use any of that, but it's one way to back up what you do. So right now we have proved, for example, that this satisfies the divergent theorem, extended Gauss divergent theorem. We have proved that they satisfy linear and nonlinear conservation laws. And we also have proven that they conserve energy in time and space, as you will see pretty soon in one of these examples. Okay, so we have this called the Brusselator, which is a heat equation. And then with initial and boundary conditions. Here is the representation. Then we go to the next step is basically you define arrays to store the components of for each of the quantities or the variables. And so then here you immediately can see that you got a Laplacian there. And it's important to notice that this is u dot square is element wise. Okay, so which is also called Hadamard product. Okay, and here is a picture. In this case, they have the right label. It's a fourth order space, mimetic, and fourth order adaptive Runge-Kutta. Okay, next we take the implicit Berger equations. This is wasn't my choice. I prefer the implicit Berger equation the standard way, but later and hopefully next time I give a talk, I will show that we can capture the shock with mimetic. Okay? But for example, in this case, we have it written in this way, which is for some purposes, this is a very good way to avoid other problems. So, and these are periodic boundary conditions, that's the initial condition, and that's the domain. In this case, we got divergence, we got the gradient, and of course, then now we put D, and this is the diagonal of U multiplied by GU equal to 0. It requires interpolation in the step of integration, and we solve the problem, and then we see, for example, in this case, there was 6th order mimetic and 4th order Runge-Kutta. And then what you can see, you can start seeing the effects of the shock right in the start. Okay. Now, this is the part that's talking about mathematics. So, for example, here is a nonlinear wave equation with homogeneous boundary conditions. Here is the wave equation, and this is the initial and boundary condition. Now, in this particular case, and by the way, in general, when you get a second order equation, the natural way to solve it with mimetic is to do it a first order system. Even though you can solve it like a second order way, it's better to, or at least I prefer, and it's more, it matches more the. Okay. So you write a first order system right there. Here are the initial and boundary conditions. And then you go and what is important here is that we have a quantity that is conserved, which is Hamiltonian. And basically, since this quantity is conserved, basically the evolution of the rate have to be zero. So you take the partial derivative with respect to time, and you end up with zero. That means it doesn't change in the process. Okay. So what we do, we take that equation, and then we write it out with mimetic operators. And then we write the discretized Hamiltonian function, and it's written this way. Okay, we can see here the quadratures, the inner products that correspond to the mimetics. And then we look at the temporal evolution of the Hamiltonian, take the derivative with respect to time, and we exactly get zero. Okay? That means the mimetic operators in space conserve it. Now, that works if you combine the two, absolutely. Okay, so in this case, we try, this is the initial condition. We have mimetic fourth order, and COM4 is a pseudo-symplectic integration method. Now, it's called pseudo-symplectic because it's only symplectic up to 6th order. After 6th order, it doesn't preserve energy, but I actually happy till even till 4, but 4 and 6, and so then we go 4th and 4th, 6 and 6, and then the other one in blue is the mimetic 4th order with the standard Runge-Kutta 4. So you look at this. Well, this has a little bit of fluctuation here, but basically they converge, all of them. But now what happened with the energy? It is actually well established that the standard Runge-Kutta doesn't conserve. Okay. But all the other methods conserve energy. You know, the mimetic with the pseudo-symplectic and the mimetic with the Runge-Kutta 4. Still, a lot of people use Runge-Kutta 4 for a lot of things, but it doesn't conserve energy. If you want to have a method or a methodology that conserves energy in time and space and is computationally efficient, I just show you which one to use.
In the previous slide, is that steady state solution? This is steady state solution.
No. That was the way the question in time. This is time and space. Yeah, no, I'm not showing any time. Don't use the solution.
So initial and which time? Is that the final time?
That I don't remember. But
okay. It's not a steady state.
No.
And you were saying that's a little bit, you said the problem, but the problem negative solution.
No, I said that the Runge-Kutta you can see here that is doing so. That's the Runge-Kutta 4.
I see.
Okay, but at the end they converge. They get close to the solution. But when you look at the energy, then, and this one is over time, then all the other ones satisfy energy in time and space. So you got there the mimetic fourth with the pseudo-symplectic, which right now cannot remember the name of the method, is like a comp. The comp no is for computational science, it's actually for compartment or something like that. And the reason we chose those, by the way, is because they are staggering time. Okay? So it really matches the mimetic method. Okay, so all of them 6 with 6, 4 with 4. So you're talking energy conservation in time and space.
So the failure to conserve energy in time, that's all the quote unquote fault of Runge-Kutta 4.
Now, there is a guy that I know for many years, David Etchison. He constructed a method that he called relaxation Runge-Kutta. And that one conserve energy. But he used a parameter. It's like a SOR for people who remember the iterative method. It has Gauss ideal, and then you get a SOR, and then you have a parameter there that you choose. In this case, he forced. By solving this parameter, he keep the energy conservation. But we wrote a paper, we comparing everything, it's true, but it's more expensive. So for sure, for a problem that has a Hamiltonian structure, that method doesn't cut it. Okay. Now this is another equation here. That's nonlinear sine Gordon, and we have an analytical solution, and here is the Hamiltonian function that we want to conserve, and here is the numerical convergence, and we got the same one. We got mimetic fourth with the symplectic integration order 4. And 6 and 6, and then we also did the Runge-Kutta. Okay. And when you go look at the energy, again, all the other ones conserve energy, but the Runge-Kutta start building up. So if you are going to solve a problem that you're interested in energy conservation, don't use Runge-Kutta. Okay? Yes.
If you try, for example, an implicit Runge-Kutta.
No, and I'm focusing in explicit method. There are some implicit Runge-Kutta who conserve energy.
Yeah, like there is the implicit K2 that can do the job.
But I forgot to say that, I'm focusing on explicit.
Because I don't know about the other two.
I don't like implicit methods unless I have to. But
the good thing is that you can take a lot of time steps.
yeah, I know.
But you pay the price of solving.
Okay. Here is another example, the Boussinesq equation. And again, you write it as a first order system. We have the conserved quantity, we have an analytical solution. And we have the numerical convergence. Everything is fine. And in this one, the slide for the energy, I don't have it. But here is, for those of you who haven't already used MOL, this is the repository. You fork the repository, download, clone the repository, enter the MOL master folder, and open example. We do have a lot of examples in MATLAB, and we are building more and more in C++. Basically, also another thing that we are also in the process. That's gonna take a little longer, but we're gonna have a version in Fortran 2018. And that's a project with some people in the Lawrence Berkeley lab. But like I said, we are in the process of making this an open source, sustainable. That's the other thing. So we want to increase users and contributors. Okay. And that's it. So, any questions?
Well,
It's the curiosity. You all purpose of developing this model and good is for spatial stuff, right? But when you compare later, mostly you compare with like a Runge-Kutta with the time.
No,
Did you compare with the like a finite difference, finite element, actual solution, or computational cost as well as solution? How do you compare?
yes.
Yeah.
For example, I'm gonna give you two examples. Okay? One, I have a paper that I can send to you, where this was a group in Barcelona. It's a geophysics group in the supercomputing center in Barcelona, and they are geophysicists. And so I went there. I've been there many times, but the first time I went and gave a talk, and then we started working in a project. Basically, was can the high order mimetics compete with high order finite element. Okay? So, and this is a problem that has an analytical solution. You're talking elastic wave with everything, anisotropy, topography, all kind of stuff. So, and they put a table with all the features that they were going to compare. So there were like 7 things. So the only at the end, the mimetic method compete with finite finite element, the higher finite element in everything. There was only one where the high order finite element was better, and that was in the topography. Because what they did for the topography, they deformed the mesh a little bit, and it's not enough. So you have to really, and they use, in there was no analytical solution, they use discontinuous Galerki as the true solution. Okay? When they compared the two, the mimetic method was 17 times faster. As a comparison there, and now final difference at the worst, we get 1 order of magnitude better in the precision of the solution, okay? And sometimes even more. I gave a short course in Argentina, and everybody was supposed to do a project. There were 2 projects very interesting. One was, and there was a senior students in undergrads, and there were faculty, and there were graduate students, but there were, I'd like to mention the 2 undergrads. One was in physics, and the other one was in math. And the one in math, she actually did a problem where you have a room with different, where space with different rooms, and you have a modem, and you want to pick where to put the router for the signal. It was an acoustic problem. It was very interesting because after she showed that was pretty good, but then there was a good discussion with the people there of what criteria you use to decide, because you want everybody to get the same. You want, so, and that's her senior project. She probably finished already because she was incorporating all this optimization into the process. The other one was a student in physics, and he chose to do a problem, a wave propagation problem that was in a book. He even said, this is in this book, and they solve it with MATLAB and find the difference. And then he gave a presentation, and then he said, I'm going to show you here a video, and it has, and he said, I have the exact solution, the finite difference with MATLAB and the mimetic. And he showed his. I just, to tease him, I said, well, you're talking about you have 3 things, but I only can see two figures, okay, in the video. And I said, well, the mimetic is on top of the solution. And the mimetic was 2 orders of magnitude more accurate than the final difference. And that's, I can find you the book because he sent me a photo of that. So, okay. We have compared this also with the Socorro-Pereiro method, which is the original method that was called mimetic that I work with. And before I call it the spinning off and doing my own thing. And I compared with them, and again, we usually get with at least 1 order of magnitude. We have compared with something called center, something finite different. There's a group with Mary Wheeler that everybody knows, and her group. And this is a paper published. We compared to that, solve the same problem. The only thing that we have some disadvantage is in the geometry. Now, in the second phase, we are proposing, and we already started moving in that direction. We are going to use, right now we use curvilinear coordinates. Now, curvilinear coordinates, it works. Okay? However, if the region is very complicated, you have to do a lot of things to be able to solve it. And sometimes it's very hard, depends on the topography. And there is something called overlapping grids. And this is actually a package that is open source, and where it produces a system of grids, and but you will only solve in a Cartesian one, but you do a series of interpolations. One of my former students used that to create the system of meshes, and then he used mole, without that, and solve a problem, different problems in one, including with a hole. Okay? And which is basically, it looks like, I think from the original thing, it looks like it's a missile or something going through something. And what we're planning to do is to incorporate that into more. They use finite volume and finite difference in this package. Our plan is to incorporate it there so that the user have the option to use more with mimetics and or finite volume. The same plan we have with Lawrence Berkeley Lab. They have a package called Tumble that use finite volume, and they use something called embedded boundary. Okay? For topography, we're planning to integrate that also in there so that people have the option. And there is also something called OpenFOAM that is the most widely package used for fluids, and it's free. And we are also going to incorporate it in that so people have the option. In the meantime, we're looking at ways for us to incorporate something similar to embedded boundaries, but not the same, and also adaptive measure finding.
What was that fluid package? Open something?
FOAM.
FOAM.
Just one thing to understand. So when we say that in the boundaries you don't lose the accuracy, but with finite differences you do that. If I be for
That's
example,
not what I said. I said
Uniform.
that our operators have uniform order of accuracy. We don't have to do anything. Finite difference, you have to do something to, and you don't even get uniform. You may be able to do, but you have to do something that is not natural.
yeah, if I solve, let's say the one Poisson equation and I put like zero Neumann,
Yeah.
you send the differences with the same order factors and then that.
Exactly. But we're talking about solving one problem. We solve any problem and we don't have to do, so that's a different.
What about non-linear boundary conditions?
So far, we depends on what problem you're doing, but basically it's the same. So the accuracy is preserved. And the problem, not linear, but the problem has a close to a singularity or something, then you lose a little bit of accuracy.
Yeah.
But they all do. The only thing is that we go from 4 to 3, not to 2 or 1.
In terms of computation time, let's say if we solve like a 5 differential equation with highly nonlinear terms mixed up, anything, and in 2-dimensional x and y, do you have a sense that how difficult it's going to be?
Well,
fast?
a former student of mine solved Navier-Stokes in curvilinear coordinates in 3D and a problem with 35 million cells in a few minutes. The computational efficiency or complexity of the mimetic is similar to finite difference. Okay? And it's very hard to beat finite difference in the time that it takes to solve a problem. So we get the same, but then we get better results and we got high order. And in finite difference, you get the Laplacian. In finite difference, can you break that into a divergence and a gradient? You don't know. I mean, I'll bet you, I don't know, like 1,000 to 1, whatever you want, that you can. It's not possible. And if you guys, are you gonna get a divergent written and you can't, so because just, you know, find that difference. If you know find the difference, you know that you can. So all the physics is here.
Yeah.
So we satisfy all the properties of vector and tensor calculus. Now, Miguel is working with some other people in exterior calculus, because the people who do exterior calculus, they satisfy everything, but it's low order, right? They cannot do higher order. So we're trying to see, basically, because that will allow us to tackle all the problems that right now we
Questions?
What is the meaning of life?
wow.
We all know the answer is
Okay.
42, of
Yes,
course.
but I forgot to say something. That there are methods which are, they say they're mimetic, but they're not fully mimetic. And I'm gonna give you an example. You know, the chameleon is hides, is use camouflage, and it's very hard to distinguish, but you could. So that is partial mimetic, but it's not. But you take a fake coral, false coral, and you have a real one, another one. Not even the people who study corals can distinguish them. Okay, that is fully mimetic. That's where we're heading. We're gonna prove that we satisfy all the properties.
Last question.
Comments, complaints,
Complaints, yeah.
compliments.
Compliments. Oh, yeah.
So it only supports MATLAB and C++, so if you wanted to use it with another language.
Well, for example, like right now,
Find it.
well, Octave, you know what Octave is, or Octave? It's an open source equivalent to MATLAB. The same folder that has MATLAB, people who don't, because MATLAB you have to pay a license. Okay? So actually, some people complain that MATLAB is not really open source, so why do we keep doing this? And the reason we created this MATLAB is because everybody here uses MATLAB. But, like I said, C++ is the kernel. We are working in one version in Fortran. And we are going to have a wrapper for Python. Python is not as, how do you call it? I don't want to insult anybody, but Python cannot compete with any of those. Okay? So, but you can actually build a wrapper, and then you use the C++ kernel, and then you got it. And there is a lot of expansion of use of Python because it's free. And basically, but it's basically like MATLAB. So whatever MATLAB does, you can do with Python, it's free. But if you are interested in a particular language, you can become a contributor and start.
Yes, time for.
So right now, Jose, there is MATLAB,
Octave
Octave.
and C++. By the way, if you are a C programmer, you can you can use the C++ library. You can call, I don't know, you know that, right? You can call that from C.
So problem usually I work is like a parabolic kind of problem with a large number of system and something like that. And my students, because I don't know, I have no idea about this method, and my students already struggle with the finite difference, finite. When you're solving PD in 2 dimensions, it's not easy. Do you suggest me to suggest my students that use this one, and then maybe ask help from you? Do you really suggest that? It's
Well,
your
not
confidence that it's better.
Not only, not from me. You
Yeah.
go into the library, you use it, you have a problem, you raise an issue, and then somebody will respond.
Okay,
There is help provided.
I'll keep doing that then definitely. Yeah, because it's always there, a problem actually. Whenever we develop PD, it's right there, complications on it.
Yes.
Okay, so right now I'm doing kind of specific question, but I'm doing like an AI thing. I'm using Python, it's just like, but PyTorch, it also has a C++. I've had it in C++, but I'm doing like a physics problem, and I think the problem is like with when you're dealing with like waveforms, you get energy loss. And I'm wondering, because I'm using RK4, and you're saying that energy loss is big.
Yes.
It's diffusing.
That is, yes. By the way, one of my current PhD students, his dissertation is in turbulence laminar flow. So, and he's also, he gave a talk here, I think, but he using machine learning, neural network kind of stuff. Why? Because with direct numerical simulation, you're not able to get all the scales. So then they use what is called a subgrid model. So it's ELS. So you do one part and the other part you model. So in that subgrid model has parameters. So he's using direct numerical simulation with mimetics, and then using that to train the neural network and all the stuff to estimate the parameters. Now, one thing that he got working complete is solving with mimetics, direct numerical simulation, the turbulence problem. Okay, and so the only thing he's told me that he's having a little problem is in the 3D with when he puts periodic boundary conditions in all the phases. And I suspect that it's a matter of fine-tuning something because we don't really have the operator with everything, but you already got the right results. And now he's gonna look into the other part.
But okay, but you're training it on.
Well, I said
on the
AI.
data. Yeah, but he's training on data, so you don't really need to combine the languages now, but I'm wondering, because I have like a framework also in C++, because like there's a libtorch, like backend for PyTorch, but I'm just wondering if it, like, I don't know, like, I'm trying to think of like the cost of like porting it.
Well, I don't
So
know,
that I can-
but I can tell you the integrators that we use. Because if you're losing energy, no matter what you do, if you use RK4, you're gonna keep losing energy.
But not just that, like, I'm also using like finite difference as well.
Well, that's another, you are 2 strikes so far.
But if I want to use more easily without having to do Python, I'm just gonna kill the speed, and I should.
You may kill the speed.
Well, because Python is just, if you try to convert code, C++ code using Python, my is that the speed.
Well, that's a horse of a different color.
Alright, so I'm thinking maybe it's worth it for me then to just use the C++ API, so that way I can just directly integrate with it.
Oh, yeah, that's absolutely.